Are you expecting anybody else, Sabrina?
I don't think so. Well, there was somebody from your lab.
Yeah,
Uh,
they're doing a NeuroPixel, like a really long recording today.
okay, yeah, then probably not.
Yeah, I got a couple people who just can't make it, but should have recorded last time, but say Livy, uh, they're excited to see this afterwards. So maybe I'll start sharing them. Do you guys see these presenter notes like this?
No, just see the slides.
Fantastic. Does it go full screen for you guys, or can you still see my Google Chrome tabs as well?
You can see the tabs.
Yeah, okay, I won't sweat that. It's a little weird.
We're
Um,
not judging.
Thank you.
Yeah, this is perfect.
Okay, let's see. Okay, yeah, so I just took a screenshot of the abstract, of course. Well, not the abstract, just the cover page, I guess. Um, so rats learn to solve a. Can you see my cursor as well? Or do I need to turn on the little laser guy?
Oh, we
It's
can see
good.
your cursors. Yeah,
Yeah, it's
it's
good.
good.
Fantastic. Okay, yep, they learned to solve a goal-directed navigation task with changing barriers. That's like a no-brainer. Replay adapts to new barriers. That looks to be true and is predictive of future behavior. I think I could spend like an hour alone just like arguing if this is true. Um, but we'll get into that. I think it's I would just maybe say it's like more predictive or more correlated with future behavior compared to the few comparisons they did with like past behavior. And then place cells are largely stable across barrier configurations. And I would just add the caveat that this is uh, comparisons in the same day. Um, and this doesn't help the clarity when they start saying, okay, so they show that the place cells in the hippocampus learn replay sequences around barriers. Okay, even after a large number of barrier reconfigurations, I don't think this bit matters. I don't know. I think they should just omit everything after the comma because they don't really do any comparisons over 90 configurations. It's all like within the same day session stuff. So this bit confused me when I was first reading it. And then by contrast, the place set fields are largely stable, potentially dissociating the stable representation of space from a powerful mechanism for the acquisition and recall of flexible memory. So I think this is a good point, and they make this point early on in the paper that replay could be a mechanism supporting flexible planning, and there's already literature looking at it being generative and not just reflective of previous experience. And this is important for our labs and this journal club because we often talk about replay being important for memory consolidation. But here's another potential thing it's doing in the hippocampus. Oops, I didn't want that to happen. Okay, so yeah, well, okay, that was a high level flying at 1,000 miles overhead. We'll get into the nitty gritty details of how this experiment was ran. So top right, you're seeing an actual picture of the arena. It's 90 centimeters squared each side, 90 centimeters. The barriers are almost what? That's like 10 inches tall, almost just as wide. They're see-through, kind of jail bar configuration. There's 12 possible locations, but they only ever populate 6 at a time. So that gives 924. 6 choose 12 is a total of 924, almost 1,000 possible configurations. And so they'll use this to produce some random, some control distributions to compare against later. So here you can see oops, I've got 6 actually outlined barriers, and then the dots are where they could be. The other 6, it's hard to see in this picture, but there's little tiny wells. I don't know if this is concrete floor or whatnot, but there's little wells where chocolate can be dispensed automatically. So that's why I've got 9 little chocolate squares here. And so what this would look like is you'd put the rat in there, you'd get some chocolate milk. This is the home trial, so this changes randomly with each session throughout the day. But let's just say this. So for this session, this is the home trial. The rat would run towards it, start eating it. Once it was fully eaten, there's a 5 to 15 second delay period. This is to encourage the rat to actually explore more. And then chocolate will start filling another random well. So they'll call these like alternate trials or away events or random well events. And so where the home well is static throughout a session, this will change. So all other 8 wells will be visited within a session. Once it's fully filled with chocolate milk, you got this LED signaling indicating which well is actually rewarded now. And so om nom nom, he eats the chocolate, and then you just alternate between another home trial. So you go home trial, random well, home trial, random well, and then you'll do that for 30 to 70 minutes, depending on the activity of the mouse that day, or rat, sorry. And then you'll do 2 to 3 sessions per day. At least that's what they were using for the comparisons for most of the data exploration. And then these sessions would be separated by just a few hours. And when the rat was not on the track for those few hours, they put it in a cage or something. And yeah, I said most, if not all, comparisons are actually between sessions within the same day. Okay, so we took him out of his rat home here, and we started another session the same day. You notice we reconfigured the 6 barriers, and then now we have a different home well is now in the top left. This is, to me, this is a very cute picture. This is a wireless hyperdrive. And so this will be 50 to 60 grams. So it's about 10% of this guy's weight. This is a, I think, 4-month-old rat, male rat. And on average, given this hyperdrive, they were able to get 156 place cells per recording session. And then they implanted this in 4 rats, but only 3 kind of worked out. Poor rat number 4 had no replays throughout the sessions. Had some place cells, but just failed at the replays. Everybody else, these other 3 looked pretty decent. A lot of replays detected per recording session. You can see this is easily like 10 sessions, and we're up into 200-300 per session. And so what they did with this spiking data is they encoded it with memoryless Bayesian encoder decoder, whatever you want to call it. So I didn't want to go through the whole derivation of this. I'm just kind of going to point out the general equations. But yeah, so what we're really going to use it for is we're going to want to get the probability that the rat is in some location X, conditioned on the spiking data in a certain time window. And if I walk through this, I'm not deriving it again, but I'll just point out we have all these things. This is a constant that allows you to turn the rest of this part of the equation into an actual probability, so you can normalize it between 0 and 1. This is the prior overall spatial position. So what's the probability that the rat is in any given spatial bin? They use a uniform distribution, so the rat could be anywhere in the maze with equal probability. They didn't have to do that, but that just makes things simpler. And then this is like the average firing rate of a cell, I believe, F. So we've actually got that data. And this is the duration of the time window. Here's the average firing rate again. So we have all this. So that's as deep as I'm actually going to get into this.
I had a question real quick.
Yeah.
This is just like a animal behavior question maybe, but pertaining to that like assumption of they'll be anywhere with equal probability in the environment, is that like like, do you think that that assumption is true though? Like, if there wasn't a reward location, there are specific places that they would prefer to be, right?
Yeah, and they like hugging the walls too. If
Yeah.
if if it's not equally lit throughout, it looked pretty equally lit. But I don't know,
Mhm.
they had enough data. Maybe they could have actually just taken a frequentist approach and actually, plugged in the observed probabilities,
Yeah.
updated that uniform prior in a Bayesian way. They could have done that. That'd be interesting to see if it changes anything. Um, and then, yeah, so what we'll end up doing though, right, if we can actually compute this, we want to look at all spatial configurations. We want to take an argmax over all spatial configurations to actually see what this Bayesian decoder would infer the position of the mouses given our recording spiking data in. And if you do this over, you just do a sliding window approach, right? The n is just over different portions of your recording session. You can get trajectories of the mouse through time, or the rat. I'm going to keep doing that. Every time I say mouse, you just know I'm going to stop apologizing for it. Let's see. Okay, so they had 100,000 candidate replay events. And so these candidate replay events would be where that Bayesian decoder, where the trajectory it would give would be kind of smooth in the trajectory, right? It would, instead of they end up rejecting when the decoder guesses that the position is changing dramatically, and I'll show some of those criteria on the next few slides. But they get these 100,000 candidate replays. It's where the rats kind of just stopped for at least 100 milliseconds, so a tenth of a second. But then we have a lot fewer actually accepted replay events. And yeah, it's because of these criteria we'll go over. I think they end up with like 4 or 5 criteria total. And this method isn't dependent on, they have 2 methods. Is that true? No, they for this method they come up with, it's also, none of the criteria has to do with sharp wave ripples coming from the hippocampus, which I guess in previous literature that was a thing. But a lot of their replays actually didn't have any dependence on sharp wave ripples, which is interesting, I guess. So we can look at some of these criteria. I got to keep moving everything around on my screen, all my Zoom stuff, right, and see. Okay, so 3 main criteria to see if they were actually accepted as replays. So the rat speed had to be less than, a couple inches per second. So it had to be stationary. The posterior spread is kind of, I'll get to that in a second, but this is coming from the Bayesian decoder over space. It's probability over space. So it's kind of like confidence. So the confidence of the decoder had to be pretty decent. There was a threshold. And then the center of mass jump size. So this is also coming from the Bayesian decoder, the trajectory. It had to be under a certain, like what's that, 8 inches, 20 centimeters. So it couldn't just jump around all over the place. So here's how you would compute the center of mass. This is just, if you just focus on like the X, right? You've got a kind of an expectation, a weighted average. We're just going to sum over all the spatial bins and the probability the Bayesian decoder gives to each one. So if we've got 2 examples here, the center of mass on the left one would be dead center, right? Everybody's kind of pulling it equally, but if we give higher probability to here, it's going to, just kind of gravitate towards it a little bit. So these red X's would be the center of masses, and we'll use these to calculate the posterior spread as well here. You see these CMs are going to be our center of masses. This is our posterior spread. So m squared. So we're going to sum over all the spatial bins, and we're going to be, let's see, how. So I think this value, the posterior spread, is this the one that is between -1 and 1? I don't think so, but this is just you can take this as a confidence metric. So it's kind of like giving you a score, a goodness of fit for the Bayesian decoder. Right, kind of like the variance of this, how big this little heat bump is. So this would have high confidence. This would have low posterior spread. Oh, I wrote SPED or whatever. I don't know what SPED is, but spread. And then this example over here, right, we got a lot more spread. The probability isn't kind of concentrated, so this would be a low confidence. So they had a thresholding on this too. Candidate replay events to be accepted had to have high confidence in their decodability. And then they also had this spatial dispersion metric, and this was to filter out stationary replays. So we had that center of mass earlier, and you're going to look at the average center of mass over the whole trial and make sure that there's kind of variance in this, that there's enough distance. So if this dispersion is 0, you'd imagine it's not going to move at all. If the center of mass at each time point is the average center of mass, it's not moving at all. So you want this d squared value, the dispersion, to be above whatever threshold you choose. Okay, any questions on the criteria? Otherwise, I'm just gonna give some actual concrete examples. Okay, I'm going forward. Here we go. So this is kind of like everything. Like this is a long sequence. I can't remember how long this is, maybe a little over a second. And if you kind of filter it, we can see this little bit over here is an actual accepted replay. And we get rid of a lot of this noise. There's not big jumps anymore across the whole arena. The rat speed here we can see is low. This horizontal line would be that 2 inches per second threshold, so we got to be below that. The posterior spread, so the confidence in the Bayesian decoder. At one point in here, it does jump high. So the green represents a candidate sequence, and then the gray is sometimes they'll just skip over. I don't know what how many they get to like skip over in an accepted replay, but they just smooth over this. So you see here the posterior, the confidence in the Bayesian decoder goes down for a second, but they'll just omit this and smooth over everything. The jumpiness again is really low throughout. We got to be below this, and then this is an actual replay where the sharp wave ripple amplitude was high, and the spike density too was high. The firing rate over this whole window was high, but they didn't use these as criteria, but they did kind of look at some of these graphs and see spike density didn't matter too much, and they didn't make too much of a fuss about the sharp wave ripple amplitude either. I don't know if you guys want a puzzle to solve. I don't know why this candidate sequence, this also wasn't a replay, because it looks to be just about the 100 milliseconds requirement. It's got a few, maybe it's got it's got 2 little frames that are skipped over, I guess, instead of the 1. Maybe there's some ratio I missed, but I don't know why this candidate sequence wouldn't also be accepted as a replay. It looks very similar, just maybe a little shorter in duration.
Yeah, I didn't fully get that either. Like it seems like if they wanted to highlight something on that figure, they should have highlighted a like obvious example of like this is not, an accept. I don't know. That was, or maybe it would have helped if they would have shown like the right side of panel A for that sequence, like what it actually looked like.
Yeah, absolutely. On the A had 2 bits to it. It had another example like this. I can't remember what the difference was there. Maybe one didn't have sharp wave ripples. But yeah, this is a mystery for you guys. Let's see. Last time was in replay repos. Okay, so these are some actual examples. So I've just got 2 slides of this. So the coloring is just early to late. So right, the rat started here. This is the red line is the actual observed behavior after the replay event. And then the replay event is shown in this kind of like colored blob. This little wheel thing is showing where the location of the rat is, and it's got a vector coming off here to show its heading when the replay was detected. So all these replays like we're in kind of the same place, but this one was at 16 minutes into the session. This one was 3 minutes later. This one was 4 seconds later, and they're all like from the same position. It's kind of interesting. The replay durations in the top right. So it kind of looked like what would you call that? Like exponential decay. Like most of the replay events were near like 200 milliseconds. And then the really long tail going out towards about a full second were the longest ones. So these are pretty representative. These are all about a fifth of a second long. You get the replay dispersion. So the confidence, I don't think you can tell the confidence just by looking at the colors of this trail, but they report what the confidence was. So again, we need this dispersion to be below a certain value, I think 20 centimeters. And then the speed of the rat was shown as well, is all very low. And then the bottom right figure, or the bottom right numbers here are showing spike density and sharp wave ripple amplitude. Again, they're limited looks at these data. They didn't make much of a fuss about it beyond like I guess there's a history in the historical precedent of really caring about the sharp wave ripples, but their method didn't see they got both replays with and without big sharp wave ripples. And then we can see, oh no, this replay dispersion, I'm sorry, I said this wrong. This is not the confidence. This is, again, how far it's actually moved, really. So sorry about that. The 20 centimeters, I think, was correct for you got to be above that value, but I just said it wrong. So we can actually see, like, if you look at this left one, this is kind of like a short trajectory, and we'll see it's got 12 centimeters here. But if I go to the next slide, this one, these two are kind of long. You can see it goes 25. So this is replay dispersion is more just like how far it went, I think. The shorter, I looked at these and it just tracks well. The shorter the replay was in the arena, the smaller this dispersion metric was.
So I guess the rate of replay is not consistent though, considering that like the 25, if I'm understanding this correctly, the 25 centimeter trajectory took like 30 seconds, and also the 16 centimeter trajectory was a 30-second event. Is that
Oh,
like,
you're looking at this is session time, so like the time within the
oh,
session.
oh, top
The
right.
durations.
Sorry.
Yeah, no, it's all good.
I was being, yeah, I was like, wait, that seems long anyways. Okay, I understand better now. Oh, but still, like the two on the right, for example, they're not that different in, like, I guess, distance, 14 and 16, but they're significantly different, I would say, in time.
14 and 16. Oh, I see. So these two,
Is that
times
like,
maybe almost what an extra 80%. So you're just talking about the number this thing, yeah. You're talking about the replay
yeah,
dispersion.
yeah, I guess I'm just wondering, like, is that expected that you, I don't know, that you see like large variations in the like speed of an event? Or am
Oh,
I
how
interpreting
fast it
that
gets.
incorrectly?
Oh, the replay dispersion is more just they mentioned in the paper just that they included this criteria just to make sure they weren't having stationary replays, so replays that like just didn't go anywhere. So kind of like it, yeah, maybe the easy way. They just want to make sure that it actually the replay is going far enough away from the start location.
Yeah, but I guess I'm asking, replay
Hmm.
dispersion can be interpreted as like the amount of distance a replay event covers, correct?
Loosely, yeah. I looked at like a handful of these to just kind of confirm
Mhm.
that before saying it, and yeah, loosely it does track.
Yeah, so I guess that was my question. It's just like if a replay event covers a certain amount of time, would you expect or a certain amount of distance, would you expect there to be like variance in the duration?
Yeah, I think you could have. Yeah, I don't think the speed bit matters too much.
Okay.
Yeah, because of the way it's computed, maybe it kind of takes that into account. I don't want to say normalizes for time, but it takes it into account. Yeah,
Mhm.
M would be the total amount of time. So it takes like kind of, you
Okay.
can think of this like as an averaging.
Okay.
So you could have a very short one, but as long as this D2 is still above the
Hmm.
dispersion amount.
Okay.
Or wait, is that true? Yeah,
Wait.
yeah, because it does take an average. It sums them all. So this is, you can think of this like an average over time.
Hmm. Okay.
Okay, that question made me think. Okay. So yeah, just some good actual examples. Thought it'd be nice to look at what these numbers actually are and then how they correspond to what they look like in the replay.
So I have um like like very simple question. So
Mhm.
how long did the rest stay in the start location before they moved? So how long was the replay measured?
Oh, yeah. So like there, how long was the replay event? This, how long did like the spiking happen in the brain we were recording?
Yes, exactly. Before the
Yes,
red moved. Yeah.
I have a slide. Maybe I can let me see. Let me see. I got a slide here. So this is all of the ones they detected. They had a cutoff of a tenth of a millisecond, and then you see the bulk of it's all around like 0.2. It's like a fifth of a second, 0.2 seconds. And then very, very few are going as long as a second.
So that's the length of like each replay, or is that the right length of like the resting period?
Uh, yeah, so for something to be a replay, the rat had to be resting, but um this would be during the actual spiking activity.
Okay. Yeah. All right.
Yeah, good question. And then so here, these ones I showed, none of these were kind of long. Like you can see
Mhm.
this top right number. So we had one that was almost half a second. This one was a quarter of a second on the right. And these were all like a fifth of a second.
All right. Cool.
Good question. So they said replays exhibited memory for the goal location and predicted the immediate future behavior of the animal. So yeah, I don't know if you guys want to have fun playing. It's like almost like word games. Uh, I think it's real. I am being really nitpicky, but it's fun to be nitpicky sometimes. For what they really showed, I think it's more fair to say like it's more correlated or it's more predictive of future behavior than previous behavior. So we can just go over that, and if that statement irks anybody, I'm happy to talk about it.
Well, there was have you seen there's a paper I just pulled it up because I think in 2021 from Lauren Frank's group that's like
Mhm.
hippocampal replay reflects specific past experiences rather than a plan for subsequent choice. And they basically say that like this is not like this whole idea of replay predicting future behavior isn't true, and it's like a um I think a lot of the paper is kind of saying that it's like the way people are measuring it or the way people are like accounting for it and the behavioral paradigms that you're seeing it in is why you're seeing this. But it's actually like if you like they had this like 8-arm maze thing that they made the maybe it was rats or mice, I'm not sure, but learn, and like they moved the goal from like one arm to another, and basically yeah, their finding was that you never really saw them the replay was not predictive of their behavior. It was reflective of like the past rewarded arms primarily.
That's fantastic. Yeah, and
Yeah.
that's a great point to bring up. I would love to. Yeah, I like the idea of focusing more on the experiment and the behavior than like everybody just being stuck with the same statistical tools or trying to make them more complicated. Yeah, I'd love to. If you think about it, send me that paper.
Yeah, I'll
Um,
send it in the chat right now. So if anyone's interested.
I can open that for later. Okay. Yeah, and like, let's see, do we have, I can just, I'm gonna skip around a little bit because of that comment. This is relevant. I think it's like, okay, so they're saying it's predictive of future behavior, but as far as like a regressor, right? If you want to regress the direction of the rat, it kind of does trash. Maybe that's a little too extreme. But like here, like let's see, they have away events. So when it's random wells, and then on the bottom they have home events, but they kind of look the same roughly. Like it, okay, 0% displacement would be perfect. Meaning the replays are like perfectly correlated with either the future or the past trajectory of the rat, the actual behavior. And then 180 would be like completely wrong. But we're like we're almost half the way there at 90 on the median of these and these. We're well over 60, it looks like. So it again, like, okay, sure, it's predictive, but there's a long way to go for perfect. Like there's so many of these replay events going on, it seems like maybe tens within a single trial, sometimes like just like a lot of them. So like they all, and they're different, they all can't be predictive. So trying to make sense of maybe that would be the next step for him, or if I wanted to be reviewer number 2 to this group, right? Like focus on, maybe you can make some metric like the sharp wave ripple amplitude or something like that is really points for the ones that are more likely to control the behavior and the motor output of the animal. And this this figure is to again, this is some of the evidence presented that it's predictive of future behavior and not past behavior, but this is very similar to what we're looking at here. They didn't explain crossings, and I had to look this up, but it's essentially showing the same thing, that you've actually got more probability of the replay predicting the actual behavior, right? The direction of the animal, more of the probability mass is right here for away versus past. Yeah, so this is again way on top, home wells on the top bottom, but they show essentially the same thing. If you're predicting future behavior, you're more likely to be correct than predict it using the replays to predict the past trajectory of the animal. Go ahead.
I just have a question. I guess when you're training an animal though to do like a very similar task, I just feel as though there's like it's hard to even separate like what is a future behavior versus what is a past behavior, right? Because like what does it mean for something? I'm not sure I fully understand that. Like, because are any of the behaviors that they would say like or maybe this is my question. Is their definition of a past behavior the behavior of like how many trials are they considering like past behavior?
Oh, that's a good question. I think it was just, I'm not certain, but my guess would be they're just like literally like reversing the trajectory.
Mm-hmm.
But that's a great question. I'm not certain. But regardless, I would hope that they would actually, yeah, they could play around with that. That'd be nice to include a longer duration.
Yeah. Yeah, because I mean, I guess maybe one way I would interpret this is that, or how I would think about it is, like on the away paths or away events, for example, like, okay, I'm a mouse, I'm gonna go to the home well because that's the place that I like am more familiar with getting a reward, right? But I go there, I don't get a reward, this time. So I'm like, I guess I recognize that it's this other type of event or this other type of like trajectory. And so maybe that's when you like replay a past experience that is still predictive of the future. I don't know. Like I don't have it fully thought out, but yeah, it seems more nuanced than this.
Yes. Yeah, and it needs to be more nuanced to get better predictive power. Like I think the fact like, okay, one is better than the other, but if they're both not very good, like it just feels like we're missing the mark. Yeah, it invites more nuance.
I might offer like a mild defense from their perspective. Which is that like the first thing is their task, it like the structure of the task, because they have like these random trials or the random away events, where the animal is homing back to a specific location, then they can say that like the end location of those replay events ends up at home more often than for whatever for the
Mhm.
past events. And at least reading the paper, that seemed like their main emphasis was just like where does the replay event end up? And the fact
That was an
that
early figure, right? Like they're just saying that was their like they're saying it's like a trial specific memory. Is that right?
yeah.
Yeah. So it depended. Yeah. So they kind of it seemed from the what were they using? Yeah, the replays. Like they had a skew. It was conditioned. You'd want to say it was conditioned. They knew what trial they were doing. They kind of picked up on it.
Yeah, that like when they knew where they were going to, like when they're going to when we're finding the random location, they don't know where they're going, so there's no reason the replay should predict their behavior. But when they are then homing back to the home location after that, then the replay more accurately predicts that they're going to end up at the home location. Or the
Yeah.
replays end up at the home location more often.
Yeah. It still feels like very far from anything causal. Like if I recall correctly, I'd still want there's still a lot of room for improvements in predictability and predictive power. But yeah, that's totally true. Yeah. They saw that statistical difference.
Yeah.
Part of it's like they just have so many replay events. I think that's a good thing to focus on the dry foam. Maybe my point is like they've got so many and they're all different. Like you just it would be nice to be able to pull it towards the more causal if you could figure out a criteria to figure out which ones are the important ones or maybe the ones the rat actually does.
I mean, just like a slight tangent here, like it's sort of interesting you say that because so what the like presumably by I mean when they expand their like replay criterion by not restricting it to instances where there's strong sharp wave ripples, they expand like expand their replay pool significantly. So who like it's I wonder whether that would change like if they had restricted it to a more classical notion, whether that would uh, uh change things. I don't know.
Maybe if rat 4 would have played well, maybe they would have had enough power to yeah, that's another great point. Did you have that off the top of your hand? How did they say or did they quantify how much that kind of like removed candidate replays? Did they say?
I don't think they said, but it surely does is significant because like they're including instances where the animal is like actually moving as opposed like when you have really strong sharp wave ripples, the animal has to be stationary.
Mhm. Oh, did I misunderstand? I think were you saying they had replay events where the mouse was like moving?
And I mean that's why their velocity threshold is like not actually zero, right? It's like I think it's like 2 centimeter. It's yeah.
It's like an inch a second. Yeah,
In principle, it can be like slightly moving.
I got you. Okay, okay. Yeah, I shouldn't have. Maybe I shouldn't have called that stop. I should have been more nuanced for sure. Um, okay. How are we doing time wise? What are we looking at? Oh, I restarted my presentation. I lost count. We're already 45 minutes in. Wow. Okay, well, I'll chug along. Okay, so they needed to make a barrier conformity metric. And so how they did that here, this confused me for a little bit, but once I realized, okay, they want to take the gradient of this kind of map in the background, the gray one. And so if they didn't have this kind of like smooth one, they just had the barrier, I think it would be hard to take the derivative of this because it would be more like an impulse function. So the reason why they make this barrier potential is they just smooth it, right? They just apply they just blur it out with a Gaussian kernel. So anywhere there's a barrier, you see the kernel has an effect to just widen the barrier, and this makes it differentiable. And so they have all these little lines on here are replay events from an individual rat, and they're color coded for barrier conformity. And they've got this equation down here, but really what it's using the cross product and the dot product of these individual little vectors with a set of like the nearest barriers. Or no, it's not. This one isn't the nearest. It's actually using the gradient. Again, they're taking the spatial derivative of this barrier potential. So without going into the details, this is really just tracking with our high level intuition of, is this thing running straight at a wall? That's going to have lower barrier conformity, right? We see this purple one. This one is going straight through the wall. So that's got -1 barrier conformity. If you're very far away from a barrier and you're going parallel to the closest barriers, that's going to be a high barrier conformity. And this makes intuition, once you kind of pull this apart, your dot product's going to be, I guess, when you're running perpendicular, that's why it's minus. This first bit is positive. That's the cross product. That's going to be when they're going parallel. So they made a metric. They just wanted to be able to put this through a computer and automate all this number crunching. And these, let's see, they ended up doing, let's see. Okay, so here they ended up making these p-values for each session. So this is the barrier conformity p-value. So here we can see the distribution of them. So most of them for the 3 rats are actually low p-values. And how they came up with p-values is, let me read this out, the caption here on D. The session average barrier conformity score for session 75, red vertical line. The distribution of scores with respect to all other possible barrier configurations. So this was shuffle. So like I said, right, you got 6 choose 12 for the barrier configuration. So you have about 1,000 different possible barriers. And so they'll use those all 1,000 possible configurations and use the current replay data and get the barrier conformity scores for all the 1,000 configurations. And you'll get a distribution like this. And then they use this is the 95th percentile cutoff. So once they make this distribution with the all possible 1,000 configurations, if it's way unprobable with respect to this distribution, they say that it has a low p-value. Yeah, so you want to be high on barrier conformity, but low on p-value. But the way they said it, I think there might have been a typo, because you see here in D's caption, they say the barrier conformity p-value for the session is the fraction of scores greater than the red line. But I think you actually want to say 1 minus the fraction of scores, because they make a big deal that 87% of these session barrier conformity values are below this p-value. But I don't think this bit confuse anybody else? Or anybody else pay attention to this?
Yeah, I think I read that and maybe I was confused, and then I didn't try to unconfuse myself, but yeah, I think it should be 1 minus or less than, I guess they could just put less than the red line as well.
If I think
Oh,
fraction
okay.
is correct, it's like the number of values greater than the red line divided by the total number of values, which will lead to a
But
small.
you want a low p-value. The way they were talking about it, seems like you want a low p-value but a high barrier conformity in D.
Yeah, but if you take the number of barrier conformity values greater than the red line and divide by the total number of barrier conformity values, that gives you a small value.
Yeah, that's true.
Well, that should just be a normalizing thing, right? You're talking the barrier conformity for each individual like replay segment, or like all possible replays, or I guess it doesn't matter. I guess it doesn't matter. I think I'm just one little twinge away from my understanding that I know what they're trying to say. Like, this is impressive that most of them are very different from the shuffle distribution. Maybe to pull myself out of the weeds for our whole everybody's sake. And then the barrier conformity. Oh, do I remember what this one was? Okay, I might have to skip over this graph. The shuffle in the previous, so the replay was more conforming to the current configuration of the barriers, and the previous configuration, it might as well be the shuffled, and that's what these horizontal lines are showing too. Maybe in the beginning, the previous and the current are looking more similar. But
It's just showing the evolution over a single session.
Mhm. Yeah, and that the previous, and that
Yeah.
it's not respecting, the replays are no longer respecting the previous configuration.
Oh,
It's immediate.
Um,
That's a good thing to bring up too. It's like immediate. There's very little ramping up. The barrier conformity is there the second you put the rats in. Go ahead, Sabrina.
yeah, maybe this isn't worth, but to pull you back into the weeds, I just it clicked in my brain. So the red line is an example session, and you're saying that this is where that session is as far as barrier conformity, right? And then your gray is your shuffled data. So you would, you would expect if it wasn't conforming to the barrier that it would be more consistent with the shuffled distribution. And so because it's to the far right, your p-value is like the scores or the shuffled distribution that has better barrier conformity compared to all of that doesn't.
Yes.
So that's why it's, yeah, the fraction of scores greater than the red line. If that makes sense. Like, because only those scores to the right of the gray line are like better barrier conformity than the actual data.
Yeah, so this is the shuffle. The gray is the shuffled data. So I think,
Yeah.
we're not,
It's
Okay, you
it's
did
like
pull me right
it's
back
like
into the weeds.
if
Go
you
ahead.
have like one shuffle out of your whatever 1,000 or 10,000 shuffles that's greater than the actual data, then your probability, your p-value is like 0.01.
But that should be a bad thing. I don't think they want to brat. They're actually not making that point with C. They're very happy that they have very low.
No, but that's a good,
p-values.
if you have one out of your 1,000 that
Oh.
is greater, that's a good thing, right? Because that means that your value is not, your shuffles are not really exceeding your actual value.
Maybe we
Oh,
shouldn't belabor it. Let's just believe them. And
yeah, I guess I want most of it. If this is my shuffled data, I guess the actual data, I expect it to be I want it all, a high fraction of them to be better than the shuffled. But yeah, again, I did get pulled right back into the weeds. I have to run away. So this is also to show, like it's immediate. You put the rat back into the new session with the new barriers, and the replays have changed dramatically. The replays are not respecting the previous barrier configurations. Maybe a little bit in the beginning, but within 5 minutes, you're back to the shuffle baseline. Okay, rat heading, I'm skipping this. So they had another metric to I guess, what would this be? Another metric to look at barrier conformity. And so they were looking at they made a time series out of the, so each one of these frames in this video would be the posterior probability of the rat being there, given that current spiking data. So you see we got a little heat map. So in this case, the Bayesian decoder thinks the rat's right here. We've got a whole list of these frames, and we'll end up doing correlations of these windowed sequences, but we'll slide them past each other with different time lags. and we'll use correlation metrics as a similarity metric. And so we take these two different sequences and start sliding them across each other, right? That's the varying betas, the varying time lags. And whatever correlation is the highest, the spike in the smooth values, that's going to be our accepted time lag. So that's what this means, our argmax over betas. So we've got a bunch of different slides we can do across each other, these sequences in time. And whatever the biggest M is, so this is going to be our similarity. We're going to assume that this is how long it actually takes the replay to get there, the rat to get there in real time, I guess. Maybe that's not exactly right. But here's the time lag maps they ended up getting, and they kind of show the same thing. They show that like the barriers are being conformed to in the replay space. So if this is the red box is a reference bin, and then we're kind of seeing how long it takes the spiking activity in the replays to become most similar to data seen like over here or over here. And it does seem to, sometimes it like peaks through a little bit, but it's a lot more continuous. This transition is a lot more continuous when you actually take out the barriers. So this is just another way to look at it, using time lags. But you can see the barriers in the time lag, I guess, is a high-level way to say this. The similarity is insanely low. Like if you look at the cross covariance here, we're talking like a millionth, 1/10 millionth. I don't know if that matters statistically. And then it's interesting also, I highlighted the peak was actually over here, but they used the peak of the smooth window. So just, if I wanted to be reviewer number 2 again, maybe I'd be like, oh, what happens if you use the absolute peak and not the smooth peak? Yeah, and my Zoom keeps getting in the way. This example is cool because if this is our reference bin, we want to go maybe here, or maybe we want to go here to the right. They're the exact same distance, but this one has a barrier in the way. And so you can see that in the time lag. This takes like half a second for the replay data to actually look similar to over here. Where if you just go to the right, the time delay between max similarity is reduced quite a bit. Okay, and then so they started looking at the rate maps and the population vectors within like a same day, between sessions in the same day. And they figured out that they're actually very correlated between sessions. They're pretty stable. So they did a similar thing where they got a shuffle distribution and compared against the 95th percentile to say if it was stable or not, the rate maps. The rate maps and were 58% of them were stable within the same day. And then when they did the same thing for the population vectors, they got 87% were stable. And so you see that here. Here's the rate maps at 58%, and here's they call them bins, right? Because population vectors are just a rate map is going to be one cell across the whole set of spatial bins, but a population vector is going to be all cells at one spatial bin. So that's why they're calling it bins here. And then we can see examples of, these are rate maps. So this would be session 1, the rate map for this cell. The rate map is stable going into session 2 for the day. And then it's also stable for session 3 where they completely remove the barriers. We've got an unstable one where this hotspot this hotspot on the left actually goes away. So these are just all examples of what a stable versus an unstable one looks like. Okay, I'm throwing more shade. I don't really have shade. I like this paper, but I'm always scrutinous like this. So they wanted to know, let me just read it here. At the same time, we wondered whether faded memories of previous barrier configurations stored in the connections between stable cells might support the occasional barrier crossing replay that we did find. And so to test this, they made a continuous attractor bump network. And then they, at modest mixing levels of old and new data, they were able to get a network that made inappropriate barrier crossings in its spontaneous replay events. And then they're claiming that this suggests that remnants of past experience encoded as connections between stable cells might act as bridges or leaks for replay to cross between directly inaccessible regions. And so, yeah, if I really want to be a jerk, I can just be like, if I were to rephrase this, it's like, okay, we made a model and it made some errors. I can make a bunch of models that make some errors. Maybe not spontaneously replay. Maybe that's the best thing about this, but I don't know if that's what their focus was.
Or I guess maybe a similar interpretation to what they're saying though is just that, I guess moving away from their like emphasis on the predictive nature of the replays that they're seeing, this is just, you're seeing past experiences being, and that's what they said, but yeah, I don't know. Yeah, I guess I don't understand how this point doesn't kind of weaken their point of like, yeah, maybe I'm not making sense. I don't know.
Oh, wait, yeah, say that. I don't know. I'm curious. What, why you thought it might weaken their point?
I guess this is evidence of, or this could be construed as evidence of just past behavior being replayed.
Oh,
Um,
yeah.
And so I guess this goes back to my point about what is considered past behavior. And if you're not considering like sessions prior to a barrier change as past behavior, then yeah, maybe you don't, I don't know, like this seems like
That makes
past
sense.
behavior. Yeah.
That makes a lot of sense. That's a great point. But yeah, they didn't focus too long on it. I guess I'm happy. The attractor networks are cool if they have the spontaneous replay and they can actually show this trajectory. But the fact that it does make some errors, I don't know. Almost anything that's not perfect is just going to make some errors. We found that the barrier. Okay, so then so some of these rate maps are stables, like 58% of them. And if they just use the stable cells, they were also able to get the barrier conformity from the time lags. So then they say that this suggests that the stable cells were capable of supporting the flexible expression of replay around the reconfigured barriers. So yeah, if they plop the mouse or plop the rat into the new session with changed barriers, they know immediately the replays are kind of respecting the new barriers, and they're able to get this respect even if they focus their analyses just on the firing of the stable cells. So that's, yeah, so they're saying that the stable cells are what's allowing this flexible expression of replay. So they show that the stability was not specific to any part of the environment, and they actually show that the decoding error goes up if you start looking at the previous or the next session. And you use let's see. Yeah, so when they're decoding the actual behavior of the animal, I guess this makes sense. This is conditioned on the current data. I think for time's sake, I'm gonna skip around.
Yeah, I'm actually gonna have to hop off now, but I look forward to watching the last 15 minutes when you share the recording. Maybe I can set up a like Google folder and we can put all the future recordings in there so they're all like in one place or something.
Oh yeah, I'd love that. I'm gonna upload it on
Okay.
YouTube too. If I do that, I can put it in that folder.
Okay, cool. Sounds good. Yeah, I'll see y'all in 2 weeks.
Bye, Sabrina. Thank you.
Bye.
Bye.
But I'm skipping over some calcium imaging data. It's this great paper from 2013. I guess it's a classic from Yiv and the Schnitzer lab. But just showing with calcium imaging what these place cells do over much longer periods. Even though they call them stable in this paper, it seems there's drift in them. That's fun to argue about if that's going to be captured in spiking data as well as calcium imaging. But just for time, I'm going to skip over that. So then they started looking at these unstable cells and trying to find correlates of why they would change their rate maps when you put them in a new session. And they noticed the PV correlations, so the population vector correlation maps and the local barrier similarity. These like kind of look roughly the same. And so, right, all you need to do to make this is anywhere where there was a change, right, you just, again, kind of make a sliding Gaussian. That's most of the work is done here. Just make this more continuous and smooth. But to make a metric out of these comparisons, right, we can talk about the barrier similarity. So when the thing really, in areas of the map where barriers changed, which I guess would be low barrier, that's actually where you had unstable cells. So when unstable cells seem to be correlated with places where the barriers changed, I guess a nice high level way to say this. And so taking this hypothesis from this graph, you would conclude that, well, maybe if we undid the change, we would go back to a very stable cell. And I think this figure supports that hypothesis. They show when they restore it, right, this population vector correlation goes way high again. And then I won't go into time for the same things going on for the rate map correlation as well. And so the unstable cells do increase their rate map correlation over time later, like halfway through the session, to be similar to the stable ones. And so what they conclude here is that there's probably two maps going on in the hippocampus. You've got a rigid cell map that's spatially invariant, it's rapidly instantiated, and it's adaptive, right? So supporting replays around the new barriers. And then you've got these slower to develop, right? This is slower to develop, unstable or barrier-specific map that codes local features of the environment. And so here, these less stable, slower to develop barrier-specific cells will remap depending on what barrier, right? This horizontal line is a barrier. So you will get remapping, but these rigid place cells don't really care. So these would be these blue stable cells we saw. And then they have this kind of synaptic diagram showing how they imagine this to be instantiated in the hippocampus. And I guess that's the end. So now would be a good time for questions. Or did anybody do a deeper dive onto this figure than me? Anybody want to add some more of their understanding?
I'm not into this whole two map thing. So like it's well known that place cells will remap when you put, for example, an object in the environment, and that like they do this when their fields are like in proximity to the object. There's no like, so like as far as I'm concerned, they just show that they have remapping in response to these barriers moving around. But there's no notion that like these are two separate maps that are somehow like kept separate as distinct entities. Like they show that that some cells don't remap and some cells remap, but that's not, I mean, unless I missed it, there's no like explicit evidence that these are like somehow two completely separate populations that are yeah.
Yeah, that's making me think. Yeah, no, that'd be a great point. I wonder if they have the data to look at that to see if they're literally, maybe one, like, yeah, maybe they're not rigidly separated. Like one place cell could sometimes have a a place field that's like barrier specific, then sometimes not. Like it could
Oh, I'm
participate
sure
in both
that's
maps.
actually what's happening is that like it just based on the movement of the barrier, you just have like the cells that are locally affected are being well, I mean, I guess like if the claim in this cartoon is that that's not the case, that there's some cells that like actually maintain stable firing. But
Yeah, I'd be interested if an individual cell could participate in both. Could be both a rigid cell in some context or a barrier specific in another context. I had maybe I'll check
actually,
my.
so they
Go ahead.
must have some kind of like so like for example, if you look at the bottom in this cartoon in the middle, the bottom left column, those cells along that barrier.
Mhm.
So like the three cells that are intersected by the barrier. They must have some like empirical evidence that says that that's a thing, right?
Yeah, some place cells in the barrier. Oh,
They
yeah,
must have
they'd have
some
to be
evidence
near
that there's
the.
like cells, place cells that maintain their all of their activity attributes, even though the barrier is intersecting them. Although I don't recall seeing that explicitly.
Yeah, and they threw away a bunch of stuff that was like too close to the barriers. I thought, at least in some of the analyses. Yeah, how do they know that? Maybe it's just a place cell or a place field around the barrier. I'm gonna check my notes. I think I had something else about this.
But in any case, I still maintain the point. I don't think that they've shown explicitly that these are like somehow two separate maps that like the brain can access separately.
Yeah, are you okay with them being like more like you so the it'd be more like continuous? Maybe that's not the right word.
Yeah, that
Or
would be my
intermixed.
interpretation is that like there's a continuum of like remapping in response to barrier, and some cells just exist like on one side of the continuum where they're not remapping that much.
Yeah. And if the what is the barrier specific cells doing as well? Like if the rigid cells already support, I guess they're saying they encode objects, like it's an object or a border cell or something.
Oh, this is like very part of because they have to work it into the existing literature. So it's like this notion that remapping is a way of encoding new memories.
Oh, rate
That like
remapping.
the idea is that like these uns quote unquote unstable cells that are remapping to the barriers, they're reflecting like the individual memories of each configuration, whereas the stable map is this thing that you can use to plan your trajectories because it's not being affected by it's not,
Oh, interesting.
yeah.
Okay,
It's
so
an interesting
maybe
idea, but I don't feel like they have explicitly shown that there's this actual separate thing that you can access separately, as
yeah,
opposed to it just being on a continuum.
yeah. Yeah, I'm just getting up to speed, I guess, on the first point. I'm glad I asked you to share your understanding of this because yeah, because I was curious, yeah, what is if the rigid cells can do the rapid replay, like what's the point? But if slowly you have developing some longer memory trace coming from the barrier specific,
Yeah.
that makes me appreciate the hypothesis more for sure. But then yeah, then to your second point, I don't know, yeah, if it's you shouldn't say they're indirectly accessible.
I don't know if they actually said that, but that's sort of the vibes that I get from like how they, I mean, I don't mind them saying it. I just, and it's an interesting idea. I just don't quite buy it from the paper itself. Like,
Mhm.
surely they will develop the idea more with further data, but
If they'd have also here, I had notes here. I don't know if you can see it in the bottom, but they could have also changed the number of barrier changes between sessions. And if this is, they should have hopefully then seen a correlation between the amount of barrier cells and how changed it was. I don't know if that would add anything to the discussion. I guess if you change enough, you should see something like, would you even see, at some point you'd instantiate maybe I don't know if you can instantiate global remapping. I don't know the literature well enough here. So maybe that correlation would have some sharp bend in it at some point. If you really went from one barrier to 12, could you have a global remapping? I don't know. They're going from 6 to 0 without, so probably not.
Yeah, I mean they're doing enough like instances. I imagine that the animal understands very well. It's like the same environment, just things are moving around.
Yeah, and they had a bunch of training sessions before they even started these 2 to 3 day recording sessions. Yeah.
Yeah.
So I don't think you'd be able to look for that kink. I was just trying to make sense. But still, this correlation, I think this does arise from what they were saying. The more barrier configurations you should have, the more unstable cells you should have.
Mm-hmm.
Okay, we're just at about time. Sabrina didn't really mention if maybe she talked to you guys offline about it, like who's going to present next week.
Well, I mean, I thought we were gonna go with this 2 week thing.
Sorry, not. Oh, it's just us. Oh, I didn't realize CD
Yeah.
left.
Well, before we go to the logistics, what did
Yeah, it's
you
every 2 weeks.
takeaways
Yeah.
from the paper?
Say it again. Albert, say it again.
Oh, what were your takeaways for the paper?
Mm, what did I guess this hypothesis, like one of like the thing you just kind of highlighted, I think is maybe drove home the point they wanted. Um, it just I guess to me, it doesn't really give me any concrete questions, but it gives me a new perspective to look at replay. I guess I'm appreciative of the overarching hypothesis that replay could play not only just a memory consolidation thing, but be doing other things as well, like flexible planning. I don't I'm kind of new to this literature a little bit, so I guess that's my takeaway. What about you?
Well, I have a vague recollection of when he presented it, like maybe like 5 or 6 years ago. And then, I mean, presumably the thing was like not yet in paper form, but the main idea was just that like replay. The main idea when he presented it, better remember, is that like replay conforms to physical uh barriers. That was more or less it. Because I mean, so like it's a very simple thing, but like it doesn't have to be the case, right? Like replay could, I mean, like one of the ideas from to the whole notion of like shortcuts, like cognitive shortcuts from Tolman is that like you don't have like your mental simulations don't necessarily have to like conform to um physical reality per se.
Yeah, and in this one, I guess they're showing it is biased towards the current, but there are still,
Yeah.
yeah,
At
illogical.
least in the context of this task, it conforms with the physical uh surrounding. And I guess they must have like if through very like more thorough analysis come up with this idea about there being two maps, which maybe not.
Well, yeah, I guess that makes, yeah, certain parts of this paper were confusing to me. I'm glad I finally, I've been meaning to read this for, I think, a full year. So maybe I would have chosen something different if I'd have known what I was getting into, but glad
That's
I
how
did
it
it.
always is.
Say it again.
That's how it always is. I mean, it's even worse when you are reviewing papers because then you just get the abstract and then you like are stuck reviewing a paper that you thought you might like, but then you just absolutely hate. That's how you become reviewer number two.
Yeah, okay. It's a shared experience.
But I mean, I guess it's just the two of us, but maybe you can speak for the others in the group. Like I would be interested to present I guess at this point it's a historical paper from 2007 um about this is the first paper that really introduced the notion of uh, I guess like planning into the hippocampal literature.
Which one is it? I'm curious.
Oh, it's I can hold on. Okay, put it in the chat.
Gotcha. Okay, let's see.
So the other thing that we haven't spoken about, in part because all the papers have been about actual replays, that there's actually like two sort of planning mechanisms. There's replay, and then there's also theta sequences, which are
Mhm.
not tied to sharp wave ripples.
Oh, so this one
So
includes
this one
both, or focuses more on the latter?
is about planning in effectively what turns out they didn't know it at the time, but it's about planning in theta sequences. So you know how there's phase precession of place cells, right? So within a single theta cycle, you have these sequences of activity. So people thought for a long time that, I mean, okay, this is getting into what the journal club would be, but people thought for a long time that these sequences were just the like byproduct of the animal's ongoing running. And this paper is the first paper to show that actually in these sequences, you can get activity that corresponds to potentially like a planning mechanism. So animals at a choice point, and you see that this activity is not actually tied to the animal's movement, but is tied to looking ahead.
Interesting. Okay. Would any of the stuff they captured with like, because in this paper I just presented, they didn't look at theta, and but they did look at sharp waves, and they had a bunch of these replay things that didn't have sharp wave amplitude at all. Could they have been capturing? Is that they were on the almost the right time scale, right? Like, is
Uh,
theta like around 8 hertz?
I think that their argument would be that, or their position would be that they're still looking at replay as opposed to theta sequences because, I mean, that's partly why they show that, like in many of the cases, they actually still see strong sharp wave ripple power and that, yeah.
But on the ones where they didn't get sharp wave ripple power, could they be seeing what should be classified as a theta sequence? I guess that's my question.
Probably not likely. I think their argument is that those are replay events that are like replay because replay is a much faster timescale than these theta sequences, uh, typically
Theta cycle is like
100 milliseconds. Yeah, they have some that span like half seconds, so those are in
but the
like
bulk are around 5 hertz.
the bulk of their events.
Yeah, the bulk of their events, the mean is around probably 0.2 something.
I forget. My
I was just
understanding.
curious. I didn't want to, yeah.
I can double check. There is like yeah, I mean, this in particular sort of muddies the distinction between the two, but
I
other
guess I was just asking to clarify for my own, yeah, understanding. Yeah.
no, I have to read their like methods a little bit more carefully to see for sure.
But I'm excited to see you present this. This will be fun, and Sabrina will be happy to hear that you're volunteering.
Okay. Yeah, no, then I can present it because yeah, I feel like it's important to have some like understanding of the history of but also I can I'll expand on it into like where it's expanded to into current day.
Yeah. Oh, this will be great. Can I ask, are you in Jay's lab?
No.
Oh, where are you
I'm
at?
in Mark Schnitzer's lab. We're in the process of or I'm collaborating with Suhi in and Jay in the because I do imaging in rats, and they're coming up with a computational model in relation to the experiment that I'm doing.
Oh, that's cool. Yeah, Sabrina was trying to get me to collab last week, and I just had to tell her right now at this point in my thesis, I feel like what limited hair I have is on fire. So it's gonna have to wait. But Yeah, Jay's got other ideas, I guess, too, in the pipelines. So wait, you said the Schnitzer Lab?
Yeah,
Oh, so that paper I linked, I kind of showed, you're probably really familiar with that? The
very familiar.
2013. That's such a good paper. I love that paper.
That's interesting.
I'm gonna throw this out here if I have another minute of your time.
Yeah.
I kind of threw it out there like just low key. I was like, maybe with like spiking data with tetrodes, you'd see different place cell drift over time, place cell representational drift, or rate remapping, or whatever you want to call it. And one area I could see that argument being true, right, is like some of our data in the lab looks like we're not sure. We've got this hypothesis floating around that the promoter for like G camps and stuff could be fluctuating over time or could be dependent on the groups. Have you heard of this? Do you guys talk about this ever at all with the G camp stuff?
We don't talk about it.
On purpose or?
Um, well, there's not that many experiments in the lab that are actually like long-term chronic, like on the order of like multiple weeks, where the stability, there's not that many experiments where like looking at stability of representation is like the explicit purpose. So like even if it is a thing going on in the background, it's better to like just be ignorant of it. Um,
Amen.
is like change in expression level a thing that happens? Yeah, it is a thing that can happen. It would be extremely hard to, I mean, the other reason to not talk about it is it would be extremely hard to troubleshoot, or it'd be extremely hard to diagnose, and it'd be extremely hard to do anything about. Uh,
Yeah, I guess the best bet in that scenario would hopefully somebody could put probes in and you'd just be able to trust that maybe a little more.
I mean, yeah, it's, I mean, so how are you gonna actually diagnose it? So like, for example, if you had expressed GCamp with a promoter, if you had expressed GFP with a promoter, you can just observe like, how is the fluorescence changing over time? And then presumably whatever change you observe is directly an reflection of expression levels. But with GCamp, you're looking at like the GCamp itself is reporting like changes in neural act or changes in calcium, right? So there's no like stable baseline that you can really compare consistently across time.
Yeah, I think for us, like somebody's analysis on the miniscope stuff, it was just like they saw with the enriched group of mice that even though I think it maybe had like sparser activity, they had more cells reported, which made them start thinking about this. But yeah. But yeah, like I get your point though. If this is usually not the focus, like these long-term changes, I guess I focus on it. I'm curious still about representational drift, so I've been thinking about this a lot.
And you're talking to exactly the wrong person because I'm like very skeptical of this concept of representational drift.
Oh, well, yeah, I keep wanting to. Okay, I'm gonna bookmark that. I gotta run away, but maybe I'll throw it in at the end
If
of
you
your
can find a
discussion.
way to like work in a journal club paper, I'd be happy. That would to present a form. Yeah, yeah, it's right.
It just adds to the plasticity stability dilemma. But I mean that's one way out of it if you just go, screw it, it's not real.
Yeah. Well, I don't know that it's necessarily not real per se, as like many of the experiments that are sort of like, for example, the Nature Neuroscience paper, is like a hallmark, is like the like foundational paper for representational drift. Um, there's a lot of like experimental caveats about that, like it specifics about how the experiment was done that raise my skepticism about like, is it actually strong evidence for representational drift? Subsequent papers, I would say, are more stand on more solid ground. Like some of the imaging experiments in visual cortex for example. But like particularly in the hippocampus, I feel like for one, there's a relatively significant difference just going between mice and rats, like the stability of place cells. I mean, if you just record with ephys, like there's a relatively clear difference in the stability of representation.
In favor of rats, I assume?
Yeah, yeah.
Oh.
And then so then it raises, I mean, okay, so then it's like if we then go to higher order species, like does the amount of drift reduce even more? And then yeah, I don't know. There's really, but I think the field has sufficiently matured that it's probably a thing in certain instances.
Yeah, I've seen. Yeah, maybe Yeah, I feel like I see like everywhere they look, there's at least one paper like reporting it in like the cortical regions at least.
Like,
But
and then the other thing is if I mean, part of it is like how you are like analytically producing the notion of a representation. Like if your criteria are very strict or less strict, that can significantly shift how these things look.
yeah, I'd love to. I'm so disappointed. This is one of the things that's got my interest recently, but I do got to run away.
Alrighty.
Thanks for staying and
Thank you,
chatting with me,
Steve.
Albert. Excited to see what you can do in 2 weeks.
Thanks for presenting.
Take care.
But